Hi, I'm Ben. I'm the founder and CEO of K-Scale Labs. We're building open source humanoid robots. If you've been following the humanoid robot space for the last few months, you've probably seen videos like this one from Tesla with some dancing, or this one from Unitree with some kung fu, or maybe this one with iShowSpeed and Engine AI's robot in Shenzhen. Um, Having been a roboticist and engineer for a while, I've been pretty amazed by how viral these videos are going. It's pretty cool to see how much progress there is in the machine learning space. But I saw something on Reddit where they thought that the Unitree video must be CGI'd, and I wanted to make a video explaining how these robots are how these robots work, how you can train a policy to do this yourself, and just give you an overview of maybe some modern machine learning techniques that you might not have seen if you're more in the classical robotics field. So this video is going to be pretty long and pretty technical. If you haven't ever trained a neural network before, I really recommend watching Andrej Karpathy's Neural Networks Zero to Hero video series, where he goes through the basics of neural network training. It's very in-depth and gives you good intuition. So once you've gone through that course, come back and watch this one. I think that if you have any kind of questions or any of what I say is not clear, you can ask on our Discord or just ping me on Twitter or something like that. I am very happy to answer and want to make sure that this comes across clearly. Selfishly, I really hope that people can train cool neural networks for our robots, and I would like to see a lot more people become humanoid robot developers. Okay, let's get started. All right, so if you've ever looked into reinforcement learning for robotics, you've probably seen some video like this. It's basically an advertisement for NVIDIA. What this is a bunch of robots running in simulation in parallel, taking actions and learning how to maximize some reward using reinforcement learning. You run these robots over a bunch of different trajectories, and as the policy that's used to run these robots gets better, it starts to go on more and more difficult trajectories until it's able to do a lot of really cool things in the real world. This is basically the heart of what reinforcement learning is you have a agent that's acting in the world. You try out a bunch of things, like you fall down a bunch, and then but as you kind of get experience from the world, you then are able to use that experience to update your policy until it's able to not fall down so much or maximize whatever other reward function that we care about. So I'm going to break this down into what this training loop actually looks like. We'll look through the code in a bit, but I want to start with the high-level overview of what these different components are so that the code will make more sense later. And also I'll give you some terminology here. So the first thing that we do is we initialize our policy. And what our policy is a function that takes in some observations about the world, and it outputs a probability distribution over the actions that the robot should take given this current observations or current state of the world. And normally we parameterize that function as a neural network, although you can, in reinforcement learning, you don't have to do that. This is deep reinforcement learning that we use a neural network. And that policy, as we sort of update it, will sort of learn to maximize the reward in the environment and learn to shift the probability distribution towards actions that maximize the reward. And we'll talk about what that means a bit later. Let me just loop this. Okay, so once we have that policy, the next step is to actually build the simulation. So you see this is one simulation running in Isaac, which is a pretty popular simulator. There's other simulators, and at K-Scale we use Majoko. This is another rigid body simulator. But the most important thing about this step is to make sure that the simulation is very accurate to the real world. If the end goal is to actually run our policy on the real robot, but the simulation is too different from the real robot, then we might be able to maximize some rewards in simulation, but it won't actually figure out how to maximize those rewards on the real robot. So there's a lot of detail in how to do this correctly. I'll dive into the detail quite a bit in the code section, but This is a very important step to do well. But once we have the policy in the simulation, then we kind of enter this training loop where we collect trajectories, which are bags of observations, actions, and rewards, and we use those trajectories to update our policy, and we move the policy to take actions that maximize the reward. We do this over and over again. I will say that this is a particular flavor of reinforcement learning called on-policy reinforcement learning, and the version we're going to use is actor-critic with proximal policy optimization. I'll talk a bit more about what those mean. But if you're new to the reinforcement learning field, you should know that there's a huge amount of literature about different ways to do reinforcement learning, and there's off-policy methods and a bunch of different algorithms, like way too many different algorithms for reinforcement learning. You can spend years on it. We're not going to spend years on it. We're going to do the thing that Unitree and EngineAI and Kscale do, but you should just be aware of that. So what a trajectory is a bag of observations, actions, and rewards. So to collect this, on each time step t, we will get the observations from the simulation. What the observations could be is like joint angles, the IMU readings, swim sensor readings, force sensor readings, anything that the policy needs to be able to predict what action it should take. We run the policy on those observations, and it outputs an action probability distribution. Normally this is a Gaussian or some other mixture of Gaussians, but basically that's just a probability distribution showing like what the policy thinks the best probability of each action should take in order to maximize whatever reward function it is trying to maximize. Then we sample from that probability distribution, and we take the action that we sample. When we take the action, we feed it to the simulator, step the simulator, and then we observe the reward now that we've taken the action. It's very important to craft the reward properly. So in this example with our walking robot, the reward could be like the forward velocity, or maybe it's the height of the robot's head to make sure that the height is above some certain threshold, not falling over. We need to find these rewards mathematically using something that we can create like a metric of in the simulation. But we usually define a set of different rewards, and then we take the weighted sum of those rewards to get a single reward value, and that reward value is the thing that our policy will learn to maximize. We do this on a bunch of different robots and over some fixed length of time to collect a big bag of trajectories. And once we have this trajectory, then we can go about updating the policy. So the first step of updating the policy is to compute what we call the returns at each time step. The returns are the discounted future rewards for that time step. So you can imagine this is like, let's say you have 2 doors, and behind each door is some additional set of doors. It's doors all the way down, but basically, like at some point, going through one door or the other door, you'll collect gold coins behind each of the other doors. But depending on, you just basically need to figure out, depending on which door I go through, what is the sort of total reward that I'll collect once I'm on the other side of that door. And we discount this, meaning we kind of multiply the future reward by some discount factor to encourage the policy to prioritize rewards that are closer in time rather than further away in time. But this is what we call the returns. Once we have the returns, then we update, we have another neural network which we call the critic, which looks at the current state and it tries to predict the value for that state. With this value function, we'll get into what that means mathematically later on, but this value basically tells you, the value of taking different actions, and we use that critic's estimate of the value to update the actor. And the point of doing that is to push the actor to take actions which have a higher value than the other actions it could take in a given situation. So one natural question that probably comes to mind is, why do we need this critic instead of just using the value from the observation directly? The reason for this formulation is to actually reduce the variance of our of each environment. So a good example is let's say we have some chess playing robot, and you could take a move, but depending on, there's a huge number of other moves you could take in the future. That one move might not make or break your game. But if you only have one sample, then you're basically saying oh, that move won me the game, or that move lost me the game. But in fact, that move basically made you slightly better or slightly worse. And so instead of just sort of observing whether or not you won that one game or not, you train a second neural network to predict like the likelihood of winning the game in the future, given that you take this move, and that model is called a critic, and that will help sort of smooth out this like crazy variance in over all these different games. And that critic gives us like a better thing to update our actor on. But once we have that critic's estimate, then we can actually update the actor, and it'll train much more smoothly. Another important detail here is that when we're updating the policy, we actually need to update the policy only until the policy is as long as the policy is close to the policy that was used to collect these trajectories. So the reason for that is that let's say as we update the policy is actually changing. So let's say I have some time step t, and I choose to take an action, and I have this estimate of, given I took that action, what is my total future reward after taking that action. And if I've changed my policy, then actually the total future reward estimate is probably different, because my policy is just different from the one that I used to collect this sort of future rewards. And if I update my policy after that, those two policies are too different, then I'm actually going to feed my policy incorrect information. So the name for this concept is a trust region, where we actually only want to update our policy until as long as it's within some trust region from our original policy that was used to collect the trajectories. Once that's no longer the case, we sort of need to go back and collect more trajectories using our new policy. And this is the crux of on-policy reinforcement learning, is that we want to update the policy using information from the trajectories that were collected with that policy. And once that policy is no longer the same policy, we need to collect more trajectories. There is off-policy reinforcement learning, but we're only going to talk about this one for now. Okay, so that's a pretty high-level overview, but I think it's more interesting to actually try to code this yourself and see a robot learn. So let's dive into some code. Okay, so this is our public repository, which you can use as a template to get started trying out RL algorithms. You can find this from our website, kscale.dev, under this RL challenge, click Getting Started, or you can just go to our GitHub page and try it out. The GitHub page has a couple of options to get started. The easiest way, if you don't have a GPU, is to try out through the Google Colab. So this will be able to run on a T4 GPU. This is a free tier version, so you can just try it out. I prefer just running the Python scripts directly because I have a GPU machine, and it helps with some visualization stuff. So I'm just going to show how to get started with that. So you can just go ahead and click create new repository from the template under myself, and we'll get started that way. Okay, so we'll go ahead and clone this repo, and then we will create a new virtual environment, activate that, and then pip install requirements.txt. I'm just running this on my Mac, so you would need to install the CUDA backend for JAX if you have a GPU machine. But because the metal bindings for JAX are pretty jank, I'm just going to leave it on running on the CPU. Okay, so the basic commands you can try just to get started is this python-m train run mode equals view. So if we run that, we can try it out. It'll basically load a empty policy and use that like random policy to run the model in the default Majoko viewer. So this is a policy that's just been initialized. It hasn't been trained. It's just taking kind of random actions. Take a bit of time to get started. If you find yourself with a bit of time, then you can go ahead and play Lichess, 1 minute bullet chess sometimes. I think when there's a video of this, you can just fast forward and skip this part. Okay, I'll just render. Okay, so this is the policy running just in the Majoko viewer. You can tell that it's not doing anything so useful, but yeah, we can visualize what the default policy is doing, how the physics environment looks like, and what the robot looks like in the environment. I happen to have a pre-trained checkpoint, so I'll show you what that pre-trained checkpoint actually looks like. We can run Python train run mode equals view, load from checkpoint path equals checkpoint.bin. This is just the checkpoint that I trained earlier. Okay, you can tell this one is able to walk forward, and yeah, seems to walk without falling over. So this is the end goal. This is a very simple policy, so the template repository is just a very easy way to get started. So it doesn't do anything so complicated, but I will walk through the code in the template repository on how exactly we can get to this point. So hopefully you can understand it, and from there do something a bit more complicated than just walking forward. Okay. So I'm going to go ahead and open up this project in Cursor and expand the screen. This KSim gem is built on top of KSim, which is also an open source library that we published. You can see the source code for it here, but I'll click through it, click through the source code in the editor here. But let's kind of just start by going through the task. So like I mentioned earlier, there's two files that matter, train.py and convert.py. We're just going to focus on train.py because that's the interesting part for training a model. I will have another follow-up tutorial where we go through actually converting the model and running it on the robot. But for now, let's just focus on actually training the model. So the way that the train.py file is structured is there's a config and a task that uses that config to actually run a model. A lot of this stuff is kind of just nice to have, boilerplate stuff to make it easy to do experiments and try out different things, keep track of what you've done. A lot of this stuff was it's all stuff that we've built at Kscale to help improve the speed of experimentation and make sure that we don't drive ourselves crazy. But if you have this config, the config just has different options for the model that we use, the different curriculum options, and some optimizer stuff. Okay, let's go and start with the first step of our diagram here, where we initialize the policy. So the model, the actual deep learning model that we use has two parts, the actor and the critic. And the actor is the policy that we actually use. In our case, we're using a GRU policy. It's a recurrent neural network instead of a multi-layer perceptron. The reason for this is that even though you can have a multi-layer perceptron based RL policy that will work relatively well, if you want to actually deploy this on the real robot, it's helpful to actually be able to do some domain adaptation. When we actually train the policy, we apply a large amount of randomization to the environment in order to match it to the real world. And in the real robot, actually, the real robot will be one sort of part of that random space. And so the RNN will actually be able to figure out what what the parameters are that most match the kind of current simulation, and it'll be able to perform better once it's kind of adapted to those parameters. This is the general reasoning for having an RNN policy. One of the features of KSim is that it makes it very easy to try out different architectures. It's basically just viewing it as a regular input-output for tensors. Very similar to PyTorch Lightning or other types of frameworks, but for reinforcement learning. So just walking through the different components, the first part that we have here is the input projection, which projects the observation space to our hidden space. We have a few RNN layers, and then we project to the output space. The output space in this case is num outputs times 3 times num mixtures. The reason for this shape is because the way that we're modeling the action distribution is as a mixture of Gaussians, where the means and standard deviations of those Gaussians are weighted by some logits as a categorical distribution. This is just a slight improvement over modeling the action space as a regular Gaussian distribution, because You can imagine that in a lot of RL policies, you might want to have the action space sort of as a bimodal distribution where like some action over here makes sense and some action over here makes sense, but the middle between those two actions doesn't make any sense as an action for the policy to take. And so you don't want to put any probability mass on that part. And if you only model it as a Gaussian, then you can only model one or the other. So that's kind of the logic. It helps with some searching, like some exploration empirically, but you can just think of this as a way to model the probability distribution of the actions. The next part that is relevant is the critic. And the critic model that we're using is also a recurrent neural network, but you'll notice that it only has a single output. And that's because the point of the critic is to only output the value prediction, which we match to our value target. We'll walk through the math for that a bit later. Otherwise, it's very similar. We just call the recurrent neural network on the input and output projections. We call the recurrent neural network on the observation space, and we output our single critic prediction. The one other thing that's important here in the forward function is this carry. This is required for the recurrent neural network. So we run this on one step, but the RNN has this carry state that we can sort of carry to the next time step. And that's very important for getting temporal backpropagation. And finally, we combine this into a single model which has both the actor and the critic. This way we can get all of the parameters for both the actor and critic to initialize our optimizer. Regarding the optimizer, we don't do anything so clever here. This is just a standard atom optimizer. It's typically a good idea to add some weight decay. Our default here is 1e minus 5. This is just helpful for making sure that the policy doesn't get stuck in some weird part of the optimization space. Okay. The next part of this task is the Majoko model. So the Majoko model is the simulation artifact that we actually use to train our policy. And we'll just open that up really quick to take a look through it. So this Majoko model is derived from our Onshape CAD model. So we try to make this fairly straightforward and physically accurate to the model that we have in CAD. The irrelevant components here are the way that we model the actuators. There's a few keywords here, like the armature, which is the inertia on the armature of the actuator, friction loss, which is, as you can expect, as you can imagine, just the friction from the armature moving. The actuator force range is the minimum and maximum torques. In our case, we have 4 different actuators. The strongest actuator has a force of 120 Newton meters, and the weakest one has 14 Newton meters. The other component that's relevant is this collision parameter. So the collisions in the MJX is a framework that we use to actually run these simulations. MJX is built on top of JAX, which is a compiled deep learning library. And because it takes some time to actually compile the MJX model, we actually, for iteration speed, reduce the number of collisions in the model, so that we only have, we don't have to compile a very large model. Every additional collision that you add adds some, extra computation that needs to be done. So in our case, we actually remove the collisions from every mesh except for the feet, and we model the feet as 2 capsules instead of as the STL mesh. This is a nice trick that you'll see in other training, like instantiations of like MJX training, to actually make the contact modeling with the foot slightly more accurate, and it just speeds up the physics engine. The other parameters that are relevant here are just a few of these parameters are around how do we model friction with the floor. I think that the right way to actually kind of, if you're doing this yourself, the right way to get these parameters to be accurate is to just run it in, like twiddle with the parameters, reference some other parameters that people have used, read through the Majoko documentation and figure out a set that makes sense. You really don't want the foot to fall through the floor. That's kind of the main thing. And you want to make sure that the foot is able to make contact with the floor and actually apply friction, so it's able to propel itself forward. But other than that, you'll see like different, kind of a wide range of different friction parameters. In fact, it's usually a good idea in your model to randomize the friction between the floor and the foot so that the robot's able to generalize to different real-world environments. But that's what most of these parameters are about. Basically contact modeling with the floor. If you dig into this, the Majoko documentation more, these parameters will probably not make more sense to you, but at least you'll feel more confident that you know what they're talking about. The last thing that's important, so let's see. We also add like sensors. So in the physical robot, it's very important to make sure that your sensors match the sensors from the Majoko model. In our case, we have an IMU, and we primarily use the accelerometer and the gyroscope. It's important to make sure that these sites are actually in the same reference frame as the IMU on your real robot. There's a common bug where your IMU might be oriented slightly differently. So that's quite important to match up. And the other input that is pretty commonly used for training RL policies is the projected gravity vector, which is typically derived on the IMU using some sort of Kalman filter. But in simulation, because can just derive this exactly from the the frame quaternion, you just apply the quaternion to the gravity vector to get your projected gravity. You actually want to add some lag to this to account for this Kalman filter lag. So that's the most important. Oh, and the final thing here is the actuators. In our case, in KSIM, we're only using torque actuators. There's a few different types of actuators in Majoko. There's a position control actuator. In our case, we actually are writing the position control logic inside the JAX side instead of using the solver in Majoko. So we just model these as we just have these as regular torque actuators, torque control actuators. Okay, so that's the first two components on our flowchart here. Next, we'll have to dive into the inner workings of the KSIM framework a bit. So we'll go into the PPO task and beneath that the RL task. You can see that the RL task loop is there's a lot of boilerplate here to make sure that to help with making it possible to run these models very quickly on in JAX. JAX is it's pretty close cousin of TensorFlow, so if you've ever tried TensorFlow stuff, you'll know that control flow stuff is pretty particular, and that's a lot of the logic here will be reminiscent of TensorFlow. But the main function here that we care about is this RL training loop step, which basically runs this collect trajectories update loop over and over again. The first step here is this unroll. So this stands for unrolling a trajectory. We basically run the physics engine with our model to actually sample from the model probability distribution repeatedly, like we described in the first section. The function to actually sample from the probability distribution is called sample actions, as you might expect. And when you implement your task, you'll need to implement this for your particular model. So in our case, we have our actor model, which we just defined earlier. The run actor function here just collects the observations from the inputs into a single vector, which we concatenate and pass to our RNN, which gives us our action distribution. When we sample, we actually have an option here to take either the argmax or sample directly. When we actually unroll the trajectory during training, we sample, but when we want to actually do inference, it's better to take the argmax or the mode of the distribution. Okay, so inside the actual function here, we have this step engine function, which you can tell there's a lot of JAX boilerplate, but the main function, the main features here are this get observation, which actually gets the observations from the MJX environment, sample action, which is the function that we defined earlier, and then step the physics engine to run the next step. Let's dig into the step function a little bit. Inside the physics engine in MJX, the main function is this mjx.step function, which takes our action and our physics model and converts the action, which is the output of the neural network, to torque commands, which we can send to our Majoko environment. The function that actually does that is this get control. So this get control function, we implement it for different types of actuators. The reason why we do this is because in practice, when we put this model onto the real robot, the actuator themselves will have a closed loop controller that actually takes the takes the output of the neural network and runs a very fast closed loop control on the actuator. So in our case, the actuators that we're using are basically PD controller actuators. The output of the neural network is the position target for this PD controller. And in practice, we take the neural network, which is running at 50 hertz. It outputs position targets at 50 hertz. Those position targets are sent over the CAN bus, which induces a slight latency. the actuator receives that command and updates its internal position target on its PD controller. If you're not familiar, a PD controller is just a, well, we can write out the equation for this. It's pretty simple. In the end of the day, the controller is outputting a torque command. So, all actuators are just torque controlled. But we have, in a PD controller, in this particular PD controller, we have this equation: torque equals Kp times target position minus current position plus Kd times target velocity minus current velocity plus some bias torque. In practice, we normally set the target velocity to be 0, and we set Kd to be the ideally damped Kd to make this sort of an ideally damped system. You can derive the ideally damped Kd parameters from the Majoko model. It's kind of a cool feature of Majoko. We choose the Kp parameters to be sort of per actuator or whatever makes sense. So on the actuators in the legs, we usually use higher Kps so that it's more responsive, and the actuators in the arms, we usually use lower Kps. This equation is actually implemented in our get control function. So the get control function takes the action, which is the output from the neural network. It gets the current position and the current velocity from our physics engine, sets our target velocities to 0. We add a slight bit of noise to our actions, just to model the real noise in the system. And then we convert to our control, which is by multiplying our Kps by our position deltas and our Kds by our velocity deltas. Finally, we clip the total control by the minimum and maximum torque. You'll see this called MIT Cheetah style actuator or MIT control. This is because it was the control system that was used on the original MIT Cheetah. Okay, so that's how we actually run our physics engine. You can look through the code yourself and get more details, but basically this is how we unroll our physics state. We apply some terminations, which are we define in our task, and later we collect these sort of full trajectories. We'll see commonly denoted in our code base is a single observation action reward pair is called a transition, and a set of transitions is a trajectory. An important detail to keep in mind here is actually how we, with an RNN model, we need to be very careful with the way that we handle the carry for the RNN. So when the robot terminates, we want to reset the carry. That's kind of what's done here. You can get some really nasty bugs if you don't handle this RNN carry correctly. So it's very important if you're actually implementing this to be mindful of what's actually happening under the hood. Okay, so that's this side of the loop. The next side is the update policy side of the loop, and this part will be a little bit more involved on the math, but it's not super difficult math, and I think if you have some intuition from the first part of the video, it should actually be fairly straightforward to follow. So in our PPO task, the main function that we care about implementing from the user's perspective is this get PPO variables function. So PPO, to implement a PPO training, we need the model to return two variables: the log probabilities of the actions that were taken, and the values, which is the output of the critic in our case. Also, in some formulations, you'll see this entropy, which is the entropy of the action probability distribution. That's a way for us to, if we add a term to maximize the entropy, we can encourage exploration. But for most cases, we can just implement log probability function. The log probabilities and the values is the thing that our model needs to return. So we'll see here, in our case, we have this model scan function. Again, this is kind of some gross JAX code, but if you can just kind of ignore the JAX part, we can look at the actual code that matters. Again, we have our run action function, which returns our actor distribution, and we call this log prob function, which is in distracts, our probability distribution library, to get the log probability of the actions that were taken under this sort of whatever the model outputs as our probability distribution. So remember, when we actually are updating our model, this actor distribution will change on each update step, while the action will be fixed. So these actions are on policy, is the term that we use, and the actor is the off policy, is kind of the one that's being updated. Well, okay, I'm probably using this notation, but basically these two, the point is that this actions and this actor distribution will be different as we update the actor. But we get these log probabilities as an array, and that's what we can use in the PPO to actually update the actor. The other thing that we do here is we get the value function. So the value is basically a single value for the current state with the observations that were provided. This also gets updated as we update the critic. The critic outputs new values for the same transition, the same trajectory. That's how we. These are the two variables that we care about for our PPO training. And another key thing here that's very important to follow is the way that we handle the carry for the RNN. We need to remember to reset the carry when the termination or the trajectory terminates, which we have this transition.done flag. Okay, so we have our get PPO variables function. Let's see where it's actually used. In our under the hood, we have this update model function, which the PPO task implements. The first thing we do is we call the get PPO variables to get the on policy PPO variables, the on policy log probabilities and value function from the critic. Then we loop over the trajectory and we update the model using these on policy variables and our sort of off policy variables that we get from the model that's being updated. So let's take a look at how that's done. Inside the model, we have this inside the training loop, we have this get PPO metrics and gradients function. The key function here, this get PPO loss and metrics, gets the PPO loss, and then we differentiate the PPO loss with respect to the actor and critic parameters and backpropagate to update them. Inside of that loop, we have this, we again call our get PPO variables on the trajectory, given the current model, which is the model that's being updated, to get off policy variables. We split the actual PPO computation into two parts, this compute PPO inputs and compute PPO loss. So let's just take a look at what those two functions are doing. Inside compute PPO inputs, we have returns. Let me make sure that I don't cover my screen. Oops. Okay, inside our compute PPO inputs, we compute a few things. The important things here are the advantages and the value targets. These are the two variables that are used to actually compute the PPO loss later on. So the advantage function. What the advantage function is telling you is basically the relative advantage of taking one action versus another action. And the way you can think about this is your critic will tell you for a given time step t, what is the value, which the value will tend towards the returns, or if we're using Monte Carlo returns, or this other thing called the generalized advantage estimate plus the values, which we'll dig into this a bit later. But you can imagine, you can picture for now the target of the value is the returns, and the critic is sort of tending towards these returns. If we just were to update our actor to try to maximize the values, this would kind of not be the right way to do it, because let's say I'm happy, I'm walking around. Any action I could take would basically be a good action. So our values are going to be high for all the possible actions. But if I'm falling over, my value is probably going to be low for all the possible actions. And you don't want your model to just sort of your actor to sort of just choose to do the high value actions, because sometimes there's a better there's a good action and a bad action, a relatively good action and a relatively bad action, but they both have high values. And the same with falling over is you want it to actually choose the thing that's most likely to do to save itself. So that's what advantages are. Advantage is basically given the different actions I could take, what is the relative sort of the best action, the advantage of taking this action instead of some other actions that I could take in this situation. This is a better way to train the actor, because it's basically you're not biasing the actor in different situations. Your actor is just figuring out the best action to do in any sort of given situation, given the cards that it's dealt. Okay, we can actually see the math for this is actually pretty straightforward. So to compute the value target, well, let's just consider this Monte Carlo returns case, although it's generally better to use this GAE term. But the way that we compute returns here is by taking the values, which we compute from the critic, and the way that we compute the returns actually is just accumulating the rewards backwards. So basically, our returns, we have our rewards backwards accumulation. The returns are sort of updated by this function. This mask is for trajectories that have terminated. And we have this decay gamma, which is a way to prioritize the more immediate rewards over the longer term rewards. This is just a very standard RL formulation. You'll notice this advantage function here is also basically accumulating backwards on our deltas. These deltas are the difference between, so the reward plus the next value minus the current value, the next value times this gamma minus the current value. This is a way to get this sort of advantage of taking one action versus the other action. It's kind of like normalizing these values by the mean of the different values for all the actions you could take. Okay, so that's the intuition. I've hand waved a lot of math, so please, if you're interested in reading this more, I think you can sit and look at these equations for a while. I just want to make sure that this video is not too long. But these are the two variables that we care about for our PPO loss function. So let's just go jump to that PPO loss function. Inside the PPO loss function, there's two parts. One is the loss that we apply to the actor, and the other is the loss that we apply to the critic. The actor loss is it's only 6 lines here. We compute the log probability of the ratio of the log probability of the on policy action, the actions that were taken under the log probability of those actions under the on policy policy versus the off policy policy. So basically, like this is saying like how much more or less does the current sort of actor prioritize some actions compared to the actor that was used to generate the trajectory. We get the ratio. So remember, in log space, subtracting two log probabilities is the same as dividing. We do some clipping. This is for numerical stability. But then we get this clipped ratio, which is basically the exponent of the log probability. It's just the normal ratio. We clip it by this 1 minus clip param and 1 plus clip param. This is a very key implementation detail for PPO. The point of doing this is to make sure that we're only updating our off policy, our sort of current model, when the ratio is close to 1, meaning when our current model is sort of outputting probabilities that are close to the policy that was used to generate the trajectory. And that's because we want to keep the on policy updates. So this is a very important feature here. But you can just read what these lines are doing. We're basically only updating when we're in that trust policy region, the trust region of the policy. The value function is actually very straightforward. We just take our current critic outputs and we try to match it to the outputs from the value targets that we computed earlier, which remember is the value targets, either returns or this generalized advantage estimate. And we just use mean squared error here, or we can use this slightly better clipped value loss term. You can read it here. Some other kind of key details here. One is it's sometimes a good idea to minimize the KL divergence between the log probabilities for the current policy versus the one that was used to generate the trajectories. The reasoning here is that you kind of want to avoid having the policy deviate too far from the trajectory policy on each step. And this is our entropy maximization loss function in case we want to encourage exploration. So those are the key implementation details for this PPO. There's PPO implementation. There's some other stuff like the metrics that we want to log and just some other kind of nice to have stuff, but this is not too important. Yeah, and all that we do is we get the gradients with respect to that loss function and apply it to the model on each step. Okay, so that's the inner workings of our RL implementation. Let's finish up the task, looking through the task here, and because this is the last stuff that we need to implement. So This is our actuator model. We're using a position control actuator, which we described earlier. This is some of the physics randomization that we apply to make sure that the policy is able to transfer to the real robot. It's actually a good idea to apply ludicrous amounts of randomization if you want to transfer to the real robot. The more randomization, the better, as long as it is still able to learn how to operate in that under those randomizers. This is some events that you can apply. So, like sometimes it's a good idea to actually push the robot to make it robust to being pushed. This will apply a push every half a second to every 4 seconds. You'll see this when it's walking around in your viewer, that it'll just randomly be pushed. That just makes the policy a bit better, a bit more robust to perturbations in the real world. The other thing is this reset function. So this is a way to reset we sort of want to apply some randomizations to the initial state of the robot so that it doesn't always expect it's going to be in the same state. In this case, we just randomly reset the joint positions and joint velocities with some noise. Another important thing is this observations. So these observation functions are all implemented in KSIM. They just are ways to derive some observation from the physics state in Majoko. Majoko has pretty poor naming. I mean, it's fine naming. It's just very hard to remember what things stand for sometimes. So you can trust that these functions are pretty well tested. If you want to implement your own, actually MJX has decent documentation for what all of these things mean. But it's pretty important to make sure that your observations are well vetted, so they actually are doing what you think they're doing. These need to be very carefully crafted so that they match the actual IMU and IMU readings on the real robot. Additionally, we can add some noise to help transfer sim to real better. Okay, this get commands function, this is something we added if you want to add joystick control as a common type of command. You want to provide different commands to the robot, and conditionally on those commands you change the reward that you choose. So you might say walk forward, and if your command is to walk forward, then you would provide some reward like forward velocity needs to be high. Speaking of that, let's talk about the rewards. So these are rewards. This is kind of like some minimal rewards for a policy to walk with some robustness. It's this naive forward reward is basically just a reward for maximizing the velocity in the x direction, which in the coordinate frame in Majoko we have x forward, y to the left, and z upward. So we always start, in our case, we always start the robot looking forward in the x direction. So this is a reward that sort of keeps the robot moving forward. And we also have a reward to maximize keeping the robot oriented towards that forward x vector using some quaternion math. By the way, an important note is Majoko quaternions use WXYZ, not XYZW. That's a very common bug, and if you're messing with quaternions in Majoko, it's very important to keep that in mind. I mean, I think most people use WXYZ, but not everyone, so just keep that in mind. Some other rewards here, stay alive reward is pretty important. So you want to make sure that if the robot falls over, you give it a large negative penalty or a large negative reward. We tried to make this kind of dummy proof so that if the class name ends with reward, the scale should be positive, and if the class name ends with penalty, the scale should be negative. That's a very common bug where you accidentally forget to set the sign of your reward or penalty, and your model learns something very weird. It's very very annoying. We tried to make this whole framework as sort of dummy proof as possible. The next section that we have here is our terminations. So the key thing for crafting terminations is to make sure that the robot doesn't terminate too early, because you want it to be able to explore and try out different actions without sort of just ending the trajectory. But you also want it to not terminate too late so that you can learn efficiently. There are some tricks you can do to sort of tune this terminations, which we haven't implemented in KSIM, but as a general rule of thumb, you should just choose a decent termination that lets the robot explore, but also terminates relatively quickly. We also have this curriculum term. The curriculum term is pretty important. So as we've kind of been going through this, you've seen these penalties and some randomizations. If you apply too much randomization or penalties that are too large right at the start of training, then the robot actually will just not learn. It won't be able to explore enough to be able to get a positive reward. So usually the way you will overcome that is by starting with sort of a low amount of randomization or low amount of penalties and increasing it as the robot becomes more capable. You could imagine too, like you would only want to push the robot after it's learned to at least do a little bit of walking. And that's what this is. We have different curriculums that you can choose from, which let you scale these kind of penalties and randomizations more or less depending on whether or not you've learned something. Like in this case, the distance from the origin is used as a proxy for how well your robot's doing. If it's able to get far from the origin, that means it's learned something. Same with like episode length, and even if you just want to be like simple, you can have this like linear curriculum that scales sort of continuously. The important thing here is that the values are always between 0 and 1, and if you implement any rewards, the curriculum will also be between 0 and 1 and the other places in the framework. Okay, that's actually pretty much all there is to it. There's a few key details, a few extra details like this model carry, which is necessary for the RNN, but that's just some boilerplate stuff basically. And yeah, the idea here is that the whole file, all of the necessary stuff for training your model is just in one file, and we can go ahead and actually run this on our. I'm just going to run it on my Mac. This is not going to be particularly performant. My Mac is just running it on CPU, so it's a good idea to set num environments to be somewhat low, let's say 8 and 4. This is not actually going to learn. If you actually want to train a good policy, you'll want to do this on GPU, but for me, I like developing on my Mac, so I'm just going to do it this way. Again, this is going to take probably about 2 minutes. MJX is kind of slow to actually compile the physics engine, so yeah, probably also a good time to play some bullet chess. I don't want to abandon the game again, so I'm not going to do it. Okay, so now we've got our TensorBoard logs. We can actually look and see what the model is training. Again, these logs are not going to be particularly good because I'm running with a small number of environments on my Mac, so the reward's not going to go up that much, but we can see a breakdown of the different rewards that the model is getting from each epoch or each set of trajectories that's collected. This shows our terminations, the sort of the episode length on average, the mean number of terminations per trajectory, and then the percent of those terminations that are caused by each type of termination. So in this case, all of the terminations are because the z position of the origin is falling below our threshold. That's what we'd expect if the policy is not doing that well. We can also see the curriculum, which starts at 0. These are some metrics about CPU usage, memory usage, some timers, and this is the PPO variables that we actually track. If you're debugging PPO loss, this is probably the most important thing to keep an eye on. I usually just stare at these graphs and go back and forth with the PPO equation until I feel like I've understood what my problem is. Actually, it's typically better to look at either the distributions tab or the histograms tab, since this will give you a better idea rather than having the scalar of the PPO variables. We also can see the trajectory that's actually getting, one of the trajectories that's getting unrolled at each step. So this is our robot that's kind of just at the start of training. It's not really doing anything, so the trajectory looks pretty bad. However, another very useful debugging feature here is to actually, for this trajectory, you can see the frame counter up in the top left corner. This frame counter matches up with these graphs. So this shows the reward over time for each frame in the trajectory. This is actually probably the most useful graph on here because it lets you tell the relative reward, and that gives you the best idea of what PPO is going to be learning to optimize for. In our case, you can tell that the naive forward reward is dominating. And a key detail here is that you shouldn't look at the absolute value of the reward. You should look at the relative value, because that tells you what the advantage is, the scale of the advantage is like to be if you are just looking at these rewards. Rather than, you can also look at our our PPO metrics here to see these advantages over time, the different PPO variables over time for a single trajectory. So I think that if you're actually developing this yourself, this is probably the most important graphs to keep an eye on. This is our push events, so this just tells you, this is some plot of the tracker that when this reaches 0, it creates a push on the robot. And some of the other stuff here, besides our rewards, we have our actions. So this is pretty useful when we actually go to deploy this on the real robot to make sure that the actions that the model is outputting here are sensible for actions to take on the real robot. I'll get more into that in another video, but that's how we can that's how we can visualize the actions for this trajectory. Also, the observations for this trajectory are pretty important to keep track of, especially if you've implemented your own observation and it's not fully tested. So, like in this case, this is a base orientation quaternion. We have our base position XYZ coordinates, our joint position observations. You can just sort of see the graphs for all of these observations here. And it's very important to, I think it's very useful to reason about what these should be from this video and make sure that they're matching up to what you expect, especially that they're matching up with the real robot. Lastly, we can see the terminations at the time that the robot has terminated each trajectory. Okay, the last panel that we care about on TensorBoard is this text panel. So we dump on each training run, we dump the config, the full config, to a YAML file that's stored in the training directory, and we also write that YAML file to TensorBoard. So this shows you the exact parameters that were used to train the model. You can use this to do sweeps over different parameters if you have multiple GPUs, and this is just very useful for keeping track of like what parameters were used for which experiments. This is the joint configurations, so you want to double check that your KP and KD values and all of the other parameters are sensible, especially that these match what you derived on your real robot. In our case, we spent quite a bit of time making sure that the parameters here that we derived are accurate and can transfer sim to real, but if you're doing this yourself, you should also consult this table. The state is just kind of the training command, and the get state is just sort of for, again, some sanity stuff and the exact versions of the packages that were installed when you ran this, and the environment variables. And finally, we have a copy of the training file. KSIM is designed so that all of the training code runs can be run in a single file. This is just very nice for reproducibility. I've been doing AI research for the better part of a decade, and this is probably the most important thing if you want to do sort of any kind of good AI training. You want to just keep track of exactly what code you ran, what caused what, all of these config stuff is just all very important. So yeah, that's what we really tried to implement with KSIM. Okay, so that's TensorBoard. By the way, we used TensorBoard instead of weights and biases because I set a lot of this stuff up when I was kind of broke and I don't want to pay for weights and biases. I think weights and biases is pretty good. I've used it before, so I don't want to bag on weights and biases, but I don't plan to use it personally. All right, yeah. The last thing I want to walk you through is our documentation. So if you do have any questions, you should ask in our Discord, but we would like to keep things in our documentation pretty up to date. So everything I've described in this video you can find in our KSIM tab under our documentation. I'll go through some of the other tabs in some other videos, but basically this is probably the main reference for just how all this stuff works in our docs. We are moving pretty quickly, and sometimes these get outdated. So if you are trying this out and you notice that something doesn't match, please just message in our Discord. The task is more details about the stuff that I've described earlier, in our environment, and some troubleshooting guides. One of the most important things, if you're running this in a headless system, you need to, in order to actually visualize our TensorBoard Majoko visualization, you need to create use this XVFB. That's just, you'll get this error otherwise. So check the docs for that. There's a nice way to add this to systemctl. Some other errors, you shouldn't experience this error. JAX I always get very weird issues with JAX nans on MJX. This was like the bane of my existence when we started doing MJX stuff. You'll see some tips on how to avoid these things. We also, have implemented a decent, debugging flow for if you do experience nans, being able to disable JIT and just run the eager mode JAX to actually see the tensor sort of magnitudes, which we describe here. Okay, so if you've made it this far, I really hope that this whole framework makes more sense, and I hope that you can try it yourself and give us feedback. We are very actively developing this stuff, and it's specifically in service of making our open source robot as good as it can be, hopefully the best in the world. I personally am very excited about the world's best humanoid robot being open source and shared by everyone, and built for developers by developers, not some other companies. So yeah, thanks very much, and I will follow up in a little bit with how we can actually go about running these policies that you train on the real robot. So stay tuned.